Hello everyone. In this video, we will be discussing topics from Module 3 and its beams and torsion of shafts. In the first couple of videos, we will be discussing about beams, and in the remaining videos, we will be discussing about torsion of shafts. So what is beams? Beam plays a vital role in the engineering applications, includes buildings, bridges, aeroplanes, and even in many different ship constructions. How beam can be defined? Beam can be defined as a long, slender structural member whose cross section is always lesser than its length. And already we discussed some topics on trusses where we got to know that truss elements are usually joined together by means of the welding, but beams here we will be connecting with the help of a hinges, welding, or both. So because of this, usually it transfers both bending moment and forces across each other. And the applications of the beam can be discussed by many methods, but in our subject we will be discussing with the help of the Euler-Bernoulli's beam theory, which is applicable even for all the beams. So before moving to the any derivations or the numericals, it is mandatory to discuss the few basic informations. So just now I told you it is since the transverse load is acting on a beam, usually it is going under the bending moment and shear force. First we will see. So let me consider a beam element where I'll be defining in both natural coordinates and Cartesian coordinates. You can able to see here. First, if I want to define in the natural coordinates, consider a beam of nodes 1 and 2, and for the natural coordinates always we need to define the coordinates as zeta. So if there is a center point, this is the origin point, means the node 1, it should be denoted as zeta equal to -1, and at node 2 the natural coordinate zeta should be equal to +1. And what is the length of the beam element which I'll be considering is 2a. It is not mandatory, you need to consider only 2a, even you can consider any other thing. If the length is considered as 2a, for the node 1 in case of the Cartesian coordinates, x is written as -a, and even at node 2 x is written as a. And here you can able to see here at the both the nodes I have shown both the Cartesian coordinates and the natural coordinates x and zeta. Since the transverse load is acting on, so how I will be denoting the transverse load? I will be denoting the transverse load as V1 and V2 at node 1 and node 2 respectively. And you can able to see the direction, any load which is acting upwards, always it is considered as positive. And since it is the discussion, I will be showing both the transverse load at node 1 and node 2 as V1 and V2, and even there will be a slope. So at each node, because of the transverse load, at each node will go under the moment. So that moment for the positive thing, I'll be considering if it is rotating in the anti-clockwise direction. So here you can able to see here at node 1, node 2, the slope, even it can be also called as deflection, it is rotating in the anti-clockwise direction. So it is denoted as theta 1 and theta 2, and even it can be also denoted in some textbooks V1 and theta 1, they can even denote it as D1, D2, D3, D4. So if you are comfortable with D1, D2, D3, D4, you can go with that. But I will be following V1 theta 1 for node 1, V2 theta 2 for node 2. Once again I will be telling you at each node there will be a vertical transverse load and even a slope. So that I will be defining it as V1 and theta 1, V2 and theta 2. The load which is acting upwards always is considered as positive, and the rotation of slope, if it is happening in the anti-clockwise direction, that is considered as the positive. So here you can able to see here the node 1 has only 2 degrees of freedom, that is the vertical displacement and the rotation. Similarly, the node 2 has only 2 degrees of freedom, again V2 on theta 2, a vertical displacement and rotation. And here you can able to see here the local coordinate system with the origin at the middle of the beam, which I explained sometime before. So since each node is having 2 degrees of freedom, so a beam which has the 2 nodes, it has the 4 degrees of freedom in total. So this particular beam we should be knowing always. We will be defining in both Cartesian coordinates and the natural coordinates. And the natural coordinates is defined as zeta and Cartesian coordinates as x. And each node will be having 2 degrees of freedom, that is vertical displacement if it is acting upwards positive, and a slope or a rotation in the anti-clockwise direction which is considered as the positive. And The finite element analysis, the process, the FEA process, how we will be considering for solving the beam problems. So first is we need to construct the shape functions, and second thing is we need to calculate the strain matrix, and third one is we will be constructing the element stiffness matrix or mass matrix or the force matrix in the global coordinate system. Will be finding out, and in the last step we will be discussing how to form the global stiffness matrix or mass matrix or the force matrix in the global coordinate system. So all these things. If you see the methodology to solve the beam problems, it is almost similar what we followed for the bar and the truss elements, except the change of the degrees of freedom and the stiffness matrix. There will be a slight variance that we'll be discussing now. So very firstly, we will be discussing about the displacement in the finite element method. So in finite element method, the displacement for an element in the written, usually the displacement will be writing it as u of x is equal to n of x into dE. So here it is not compulsory, it is always, it should be u of x or n of x or dE, need not be. Even some derivations and some topics, instead of the u, even we have defined it as v. And even some topics, shape functions, even we have instead of the n, m also we have used. And d is again the vector displacement. If you are not comfortable with the d, even you can go with ue or any other thing. So first, u of x, which is nothing but the approximated displacement within the element, and second one is the n, that is the shape function. So this function approximate displacements within the element by just having displacements at two nodes, that is dE. So dE in the previous slide we discussed. So for the beam element, what we considered, which has the two nodes 1 and 2, the nodal displacements and the rotation can be written as v1 theta 1 and v2 theta 2. v1 theta 1 for node 1, v2 theta 2 for node 2. So usually when someone is studying this one, what is the question they should get in their mind is, what is this n of x? How to find out this n of x? That we will be seeing in the next slide. So it is always convenient if the same functions are derived from a special set of local coordinates. So local coordinates means here I am talking about the natural coordinate system, that is considering a center point which is nothing but the origin. From that, where we will be defining the left node and even the right node. So the natural coordinate system is the dimensionless, has its origin at the center of the element and is defined from -1 to +1. Here you can able to see here the same thing I have shown here, whatever we discussed in the previous slide. So just have a look on this one. So node 1 v1 theta 1, node 2 v2 theta 2, length of the beam element is 2a, and the Cartesian coordinates x is equal to -a, and at node 2 x is equal to +a, and natural coordinates zeta equal to -1, and natural coordinate at node 2 is zeta equal to 1. And if you are not comfortable with v1 and theta 1, go with d1 d2 and d3 d4 for node 1 node 2 respectively. Next, the relationship between the natural coordinate system and the local coordinate system can simply be given as a scaling function. So when you are solving any derivations or any problem where it is mandatory to convert the natural coordinates into Cartesian or else Cartesian from the natural coordinates, we will be following this particular equation, that is zeta is equal to x by a. Remember this one, because most of the derivations we will be solving in the natural coordinates. Ultimately we will be converting that into Cartesian coordinates. While we are solving the problems usually they give in the Cartesian coordinates, but when we are finding out some solutions where it should be converted into natural coordinates. So always remember this particular equation, that is the conversion of the natural coordinates to the Cartesian coordinates. So zeta is equal to x by a. Since we have 4 degrees of freedoms for the element, we need to find for shape functions, we assume a displacement within element has the form. Here you can able to see here, since we have the 4 nodes, always we know how to write the shape function equation. So 4 nodes means I will be writing the 4 constant with the corresponding the coordinates. Since the natural I will be using the polynomial coefficients, here I will be defining it as zeta 0, alpha 1, alpha 2 and alpha 3. If you are not comfortable with alpha, go with a0, a1, a2, a3, which we followed for the previous derivations. Even we can go with that. And here instead of the x, here I will be going with zeta square and zeta cube. And where zeta is nothing but x by a, because it's in the previous slide we discussed. So the vector of the polynomial basis functions, how it can be defined. Here you can able to see here, this is how I have defined. So I will be keeping all the vectors in one form with the constant in the another vector form. So here it is 1 zeta square and zeta cube, and if I am taking out this from this equation, it will be alpha naught, alpha 1, alpha 2 and alpha